So we're going to continue the conversation about apoptosis we began in class but never finished. And just a reminder, different kinds of apoptosis that a cell can be going from. It can be extrinsic, where the signal is coming from outside the cell, and that's not where we're going to be coming from now. Or the signal can be intrinsic, where internal signals are actually signaling the cell to undergo apoptosis. So let's just review a couple molecules that are involved in apoptosis. The first of these is executioner caspases. Also, stands for apoptosis protease activating factor. And finally, IAP, or inhibitor of apoptosis. Can I give you an idea where those are? Up here you have IAP. Connected to this is you have 3 executioner caspases. Caspase 3, 6, and 7. And over here on the side, you have APAF. So, begin this process, what will happen is some stressful stimuli is going to cause 2 proteins, BAD and BAX, to bind to the outside of the outer membrane of the mitochondria. So these 2 guys up here, BAD and BAX, are going here and bind to the mitochondrial outer membrane. And these cause this thing to happen called mitochondrial membrane permeabilization. What happens is that a lot of holes get punched in the mitochondrial outer membrane, and the membrane depolarizes and becomes permeable. So all of the charges that are in there start to spill out, and you get special channels that become formed in there, and you start losing the contents from inside the mitochondria to the outside. One of the contents that you end up losing is cytochrome C. This leaks out of the mitochondria. Normally, it is blocked by another protein called BC, which sits on the membrane and generally prevents apoptosis. So again, once we have BAX here that are good and permeabilize the membrane, all this cytochrome C is going to come pouring out of here, out into the cytosol. Also, what happens along this is another protein complex called SMAC Diablo is going to leak out as well. So we also have ATP formation in the mitochondria stopping. That's because if you do cytochrome C inside the mitochondria, you're going to be losing the ability to form ATP. So here we have again SMAC Diablo here, and this is going to also be coming of and dumping out. Now, SMAC Diablo bind to inhibitor of apoptosis, or IAP, and so that IAP can no longer bind and inhibit the executioner. So we have SMAC bind to IAP, and IAP losing its executioner caspases. Then cytochrome C is going to combine with 1, and this is going to form a thing called the apoptosis. What happens is cytochrome C binds with APAF1, and then APAF1 binds with a lot of other APAF1 to make kind of this wheel of death called the apoptosome. So we get cytochrome C here binding to the APAF1, and then multiple APAF1 associating together to get the apoptosome, this thing right here. So you get 7 of these APAF1 binding together and really making this thing called the apoptosome. So the apoptosome then activates this thing called caspase 9, which we haven't talked about yet. And in turn, caspase 9 will activate caspase 3, 6, and 7, the executioner caspases. Now, just as kind of a little side, why are they named caspase? Well, it's kind of a mouth thing. So the C stands for cysteine because there's a cysteine in the active site of these proteins. The ASP or ASP comes because it cleaves proteins where there's a aspartate residue. So C for cysteine in the active site, ASP because cleaves at aspartate, and ACE because enzyme. So caspase. So here we go. We this is going to bind to APAF1 and become activated, and then is going to activate caspase 3, 6, and 7. So here we're getting to caspase 9 to the APAF and becoming active, and then bind to and activating 3, 6, and 7. So caspase 7, the XPQ capases cause cell death through a variety of ways. One of the things that they do is cause DNA fragmentation, so chopping up all the DNA. They also cause organelle disintegration, so essentially having all the internal organelles dissolve away inside the cell. After this happens, you change in the cell shape and form. They start to kind of become more globular and swell up a little bit, and it loses its adhesion to the adjacent cell. It becomes separated from adjacent cells and eventually lyses and is no more. Another thing that will cause the final destruction of this and bring about kind of the cleanup of this is a thing called the eat me signal. The eat me signal is by oxidized phosphatidylserine on the outer plasma membrane, signal for the cell to be engulfed by white blood cells and cleaned up. Phosphatidylserine oxidation, this is triggered by cytochrome C. So that release of cytochrome C from the mitochondria also starts to oxidize phosphatidylserine, and then those go and signal for white blood cells to consume that cell. So this kind of leads to a thing that there is some condition apoptosis is not working, and one of the primary ones is cancer. So cancer cells are resistant to apoptosis. They don't die when they're supposed to. So what makes their mitochondria different that's not undergoing this? So just to kind of back up, what often happens during cancer is you have rapid growth and proliferation of cells. And this leads to hypoxia because the vascular system cannot keep up. It can't continue to supply this growth of cells with blood. You don't have angiogenesis happening at an appropriate rate. And what this causes is hypoxia. It's not getting enough oxygen because they're cut off from the blood supply. Now, normally cells that undergo long-term hypoxia are going to die, but that doesn't happen in mitochondria. And this happens because of two different things. Number one, they upregulate their glycolytic pathways. So, if you remember, if you're undergoing glycolysis, and just glycolysis, that doesn't need oxygen to form ATP if you're not worrying about running Krebs cycle and electron transport chain. And this is happening because we have an increase in HIF1, which is hypoinducible factor 1. Now, when you upregulate glycolytic pathways, one element of glycolysis, hexokinase, you remember the first enzyme in glycolysis, is going to inhibit mitochondrial membrane permeabilization. So it's stopping bad and BACs from doing their job, and so we actually don't get this entire cascade that we just talked about starting as readily as it would otherwise. Additionally, we're using these anaerobic pathways, glycolytic pathways, to create our energy. The cell no longer needs mitochondria because it's not getting oxygen. The mitochondria aren't really doing anything. So there's a downregulation of mitochondria, which means that they don't really have the mitochondria that they need to undergo this internal signal, this apoptotic pathway. Okay, that is it. I will see you again when I get back from the conference, and hopefully this was enough learning for you for the meeting.